Alright, in this video we're going to be looking at matrix solutions to linear systems. And out of that section we're going to be writing the augmented matrix for a linear system, perform matrix row operations, and use matrices and the Gaussian elimination to solve systems. We'll start off with some basic definitions here. We'll start off with a definition of a matrix, and the plural for that is matrices. A matrix is nothing but a rectangular array of numbers arranged in rows and columns. And as you can see here, this is an example of what a matrix looks like. Here we have rows and columns, and each number inside the brackets has a special name. It's called elements. So each of these individual numbers are elements of this particular matrix that you see here. And of course, it's in rows and columns. So here we have a 2-row, 6-column matrix. 2 rows, 6 columns. That's called the dimensions of a matrix. All right, the next definition we'll look at is an augmented matrix. An augmented matrix has a vertical bar that separates the columns of the matrix into 2 groups. The coefficients of each variable, usually x and y, are placed to the left of the vertical line, and the constants are placed to the right. And if you have any variable that's missing, then its coefficient will be 0. So let's look at a couple of examples of what an augmented matrix looks like. All right, let's say we have this system of linear equations here. On the left, you have 3x plus y plus 2z is equal to 31. X plus y plus 2z is equal to 19. And x plus 3y plus 2z is equal to 25. That's the system of linear equations. On the right side, you'll see the augmented matrix for that. On the left side of the vertical bar are the coefficients here for x, y, and z. The first column represents all the coefficients of x. The second column represents the coefficient of y, and the third column represents the coefficient of z. And the column that's after the vertical bars represent the coefficients. And usually this vertical bar represents the equal sign, because that vertical bar separates the coefficients of x, y, and z from the numerical coefficients that follow, or the constants. Another example would be this: x plus 2y minus 5z is equal to negative 19, y plus 3z is equal to 9, z is equal to 4. That's the system of linear equations, and the augmented matrix is this. For the first equation, the coefficients will be 1, 2, negative 5, and then the constant after the vertical bar is negative 19. Now notice in the second equation, y plus 3z is equal to 9. Notice the x term is missing. So here we put a 0 here for the coefficient of x. And then for the coefficient of y will be 1, the coefficient of z will be 3, and 9 is your constant. Now in the third equation, z is equal to 4. The x and the y are missing. So we put a 0 for the coefficient of x in this column, and in the second column, we put a 0 for the coefficient of y. But for z, it's going to be 1 as its coefficient, and 4 is the constant that goes there. So as you can see here, if you have any missing terms, you have to compensate that with zeros as the coefficient, as in this particular example. Okay, now let's look at this system of equations here. We got this equation: x plus y plus z is equal to 14. Then x minus 2y minus z is equal to 13. 2x minus y minus 2z is equal to 5. We want to determine if this ordered triple, 10, negative 7, 11, is a solution of this system. And in this case, ordered triple means you have an x, a y, and a z coordinate. And you want to determine if that ordered triple represents the solution to that system of linear equations here. So what I'm going to do is pull out a blank sheet of paper so that we can work this out. Okay. Now the ordered triple that we're looking at is 10, -7, and 11. And we want to use those systems. We have to replace the x, y, and the z in each one of those linear equations to determine if this system, if that ordered pair represents, is a solution to that system. And they all have to be true in this case. The left side must equal to the right side for all three systems of linear equations here. Let's start off with the first one. X plus y plus z is equal to 14. Now in this case, this ordered triple, 10, -7, and 11. In this case here, x is 10, y is -7, z is 11. And in this case here, we want to replace the x, the y, and the z in this equation with those coordinates. So here x is 10, so that'll be 10 plus y is -7 plus z, which is 11. That sum should equal to 14. Okay, now if you add 10 plus -7, that's going to give you 3, plus 11, that should give you 14. And if you add 3 and 11 together, you would get 14. Okay, so we can see here that 10, -7, and 11 is a solution to this system, to this equation. However, we got to test the other two. The second one is x minus 2y minus z equals to 13. We got to check to see if this ordered triple will satisfy this equation. Okay, so here x is 10, so we got 10 minus 2 times y, which is -7, minus z, which is 11. That should equal to 13. Now let's simplify the left side. Let's bring down that 10, and then minus 2 times -7 would be a plus 14, minus 11. That should equal to 13. Now add 10 and 14 together, you'll get 24 minus 11. That should equal to 13. And if you subtract 11 from 24, you'll get 13, which does equal to 13. So in this case here, the second equation is where 10, -7, and 11 will satisfy this equation. Okay, we got to look at the third one, which is 2x minus y minus 2z is equal to 5. And again, we replace the x, the y, and the z with 10, -7, and 11, respectively. So we got 2 times x, which is 10, minus y, which is -7, minus 2 times z, which is 11. That should equal to 5 on the left side. Now, if you multiply 2 times 10, that's going to be 20. Minus a -7 will be plus 7. And then minus 2 times 11 will be minus 22. And that should equal to 5. Add 20 plus 7, you'll get 27. Minus 22, that should equal to 5. And 27 minus 22 does equal to 5. Okay, so here, that ordered triple does satisfy that third equation. As you can see, the ordered triple satisfies all three equations. So we can conclude that 10, -7, and 11 is a solution to this system of linear equations. Okay, so that's how you test or determine whether a ordered triple is a solution to a system of linear equations. Okay, now let's look at the next thing. Okay, here's an example that we'll look at. Let's say we want to write the augmented matrix for the system of linear equations. In this case, we got 9x plus y plus 7z is equal to 4. 3x minus 8y minus z is equal to -7. x minus 2y minus 2z is equal to negative 5. And here we want to just write an augmented matrix for the system of linear equations here. So in this case, I'll rewrite the equation for the system of linear equations here. 9x plus y plus 7z is equal to 4. Then 3x minus 8y minus z is equal to negative 7. X minus 2y minus 2z is equal to negative 5. Okay, so that's the system of linear equations that I want to write an augmented matrix for. So here, this is the augmented matrix which has brackets. I'm going to have a vertical bar that separates the coefficients of x, y, and z from the constants. In fact, that represents the equal sign. And then I'll just write down, for the first equation, the coefficients. For 9x plus y plus 7z, the coefficient of x is 9, so I write down the 9. The coefficient of y is 1, and the coefficient of z is 7. My constant is 4, so the 4 will be behind the vertical bar. And I'll do the same for the other two. For 3x minus 8y minus z equals negative 7, the coefficient of x is 3. The coefficient of y is negative 8. The coefficient of z is negative 1. Pay close attention to your signs here. And then the negative 7 will be behind the vertical bars. And then for x minus 2y minus 2z is equal to 5, the coefficient of x is 1. The coefficient of y is negative 2. The coefficient of z is also negative 2. And the negative 5 is after the vertical bar. So this represents your augmented matrix for this system of linear equations. Okay. All right, another example we'll look at is this. Let's say we want to write the augmented matrix for this system of linear equations here. Here we got x minus y plus 8z is equal to 5. Y minus 12z is equal to negative 11. Z is equal to 4. Okay, so again, we'll do another system of equations. I'll go ahead and rewrite this. Write this on the same sheet. X minus y plus 8z is equal to 5. And then y minus 12z is equal to negative 11. Z is equal to 4. Okay, that's my system of linear equations. So here in this case, we'll do a set of brackets. The vertical bar represents the equal sign. We write down the coefficients for each of these linear equations here. X minus y plus 8z is equal to 5. The coefficient of x is 1, so we write that down. The coefficient of y is negative 1 because of the minus sign in front of it. For 8z, the coefficient of z is 8. And then the constant is 5 that goes after the vertical bar. Now look at the second equation. Y minus 12z is equal to negative 11. Notice there is no x term in this problem. So in the first column, which represents my x's, I have to put a 0 here because I don't have an x term. So I have to compensate that by putting a 0 there. But for y, the coefficient is 1. For z, the coefficient there is negative 12. And negative 11 is my constant that goes after the vertical bar. Now the final equation, z is equal to 4. There is no x and there is no y term in this equation. So a 0 goes here for the x coefficient. Another 0 goes there for the y coefficient. But for z, the coefficient there is 1. And the constant is 4. Okay? So that is my augmented matrix for this system of equations. Okay. Alright, this time we're given an augmented matrix and we want to write the system of linear equations that is represented by that augmented matrix. Now here we got the augmented matrix 4, 0, negative 3, negative 17, 0, 1, negative 6, 14, 9, 7, 0, 2. And here we want to write the system of linear equations that's represented by this augmented matrix. Okay, so here's what we're going to do here. Now I'm writing this column by column. Okay, that's the augmented matrix here. And we want to write this as a system of linear equations. Now the first column, as you recall, is your x. The second column is the y. The second column is your z coefficients. And this represents your constants. Okay? So for this first row, 4, 0, 3, negative 17, that 4 represents the coefficient of x. So that would be 4x. The 0 is the coefficient of y, so we don't have to write down 0y. But for this 3, that represents your coefficient of z, so it'll be 4x plus 3z. Then that vertical bar is your equal sign, and then your constant, negative 17. That's your first equation from this first row. 4x plus 3z is equal to negative 17. Second row, the same way. Here there is a 0 there. That means that the coefficient of x is 0, so we don't have to write that down. The 1 is your coefficient of y, so we just go ahead and write down the y, or 1y if you want to. The negative 6 is your coefficient for z, so we can say minus 6z equals your constant of 14. And then finally, for this last row, 9, 7, 0, and 2, the 9 is your coefficient of x, so that's 9x. The 7 represents your coefficient for y, so that's plus 7y. Your 0 is the coefficient of z, so you don't have to write down 0z, and that's equal to your constant, which is 2. So this is your system of linear equations from that augmented matrix. 4x plus 3z is equal to negative 17. Y minus 6z is equal to 14, and 9x plus 7y is equal to 2. Okay, so that's your system of linear equations represented by that augmented matrix. Okay. Let's talk more about these augmented matrix here, because with an augmented matrix, our goal here is to produce a matrix with ones down the diagonal from the upper left to the lower right on the left side of the vertical bar, which is called the main diagonal, and we want zeros below the ones. Okay, because we're going to be doing some things that we're going to be solving a system of equations by using what they call augmented matrix here. Okay, so to do that, we want to produce a matrix with ones down the diagonal from the upper left to the lower right hand corner of the vertical bar, on the left side of the vertical bar, and that's called your main diagonal. And you want zeros below those ones. And here's an illustration of just that. Okay, so this is what the matrix will be of this form, where A through F are going to be real numbers. Here, the ones are along the main diagonal from the upper left to the lower right. And there are going to be zeros underneath each of those ones. Because for this one, in the first column, you're going to have 2 zeros here. In the second column, we want the 1 in the center with a 0 below it. Okay? Now, when we do this, the third row of this matrix will give us the value of one variable. Usually, it's going to give us the value of z. To find the values of x and y, we're going to use what they call back substitution. In other words, we know if z is equal to this constant, we can replace the z with that value in the second equation to find out what y is. Once we find out what y is, we'll substitute the value of y and z in the first equation to find out what x is. That's what we call back substitution. And we're going to use what they call matrix row operations. A matrix with ones down the main diagonal and zeros below the ones is said to be in row echelon form. Okay, so if you looked at that last sheet that I had, this is an example of a system of equations that will be in row echelon form because you want ones along the main diagonal and zeros underneath those ones. That's what we call row echelon form. And to get this in row echelon form, you want to use row operations on that augmented matrix. And these are the following procedures for a row operations that represent the system with the same solution set. In other words, two rows of a matrix may be interchanged. Okay, because you can interchange or swap either the first and the second row, or the second and the third, or the first and the third. And then second, the elements of any row may be multiplied by a non-zero number. And then number three, the elements in any row may be multiplied by a non-zero number, and these products may be added to the corresponding elements in any other row. Okay? And then you have two matrices which are row equivalent if one can be obtained from the other by a sequence of row operations. Okay, so to summarize all this, each matrix row operation can be expressed symbolically as follows. You can interchange the elements in the ith and jth row. That means row I can be interchanged with row j. Or number two, multiply each element by the ith row by a constant called k. So you can take k times row sub I. And then number three, add k times the element in the ith row to the corresponding elements in the jth row. That means k times row I plus row j. Okay. Now let's look at this particular situation here. We're going to use this matrix here to perform each indicated row operation. Okay, so here we got the matrix here: 4, 12, negative 28, 1, 6, negative 3, 7, 3, negative 3, 2, 1, and negative 9. And we're going to perform these operations. We want to interchange row 1 and row 2. And then in part B, take 1/4 of row 1. Part C, take 3 times the second row and add it to row 3. Okay, so we're going to do each one of these one at a time. Okay, so let me get a sheet of paper. Okay, so here is the matrix that we're dealing with. And I'm just going to write this column by column. 4, 1, negative 3, 12, 6, negative 2, negative 20, negative 3, 1, and then 8, 7, negative 9. So that's the matrix right there that we're dealing with. And what we want to do in part A is to interchange row 1 with row 2. That's what this symbol means. Interchange row 1 and row 2. So that means we're just going to swap those two rows. So in other words, here's my new matrix that I'm going to come up with. And in this case here, this first row becomes the second row. The second row becomes the first row. So when I write this, the 1, 6, negative 3, 7 will be in the first row, and the 4, 12, negative 28 is the second row. And this is my third row. It stays the same. Okay, that's all there is to it. So here what I did was interchange these first two rows to come up with this new matrix right here. Okay, so that was part A. Part B is taking 1/4 of row 1. So let me go ahead and rewrite the original matrix that I started off with. Okay, that's the matrix that I started off with. I'm going to take 1/4 of row 1. So this is part B that I'm doing. So in this case here, my new matrix is going to be this. I'm taking 1/4 of each of these elements in row 1. So if I take 1/4 of 4, that's going to be 1. 1/4 of 12 is 3. 1/4 of negative 20 is negative 5. And 1/4 of 8 is 2. Okay, and that's all there is to it. The rest of these numbers I can just bring over. This row is still 1, 6, negative 3, 7. The third row is still negative 3, negative 2, 1, and 9. Okay, that's the new matrix after taking 1/4 of row 1. And then finally part C. Okay. I'm going to rewrite the original matrix that was given to us. But this time I'm going to do 3 times the second row, and I'm going to add that to row 3. So row 3 is going to change because I'm taking 3 times row number 2, and I'm going to add whatever it is to row number 3. So row 3 is going to change. The first 2 rows are going to stay the same. So here this will still be 4, 12, negative 20, and 8. The second row is 1, 6, negative 3, 7. Okay, now this is what I'm going to do here. I'm going to take each element in row 2, multiply it by 3, and then add that to row number 3. In other words, in row 2, I have a 1. Take 1 times 3, that's going to give you 3. Add 3 to this negative 3, you're going to get 0. Okay? And I might need to do this on the side here, because this is negative 3 times row 1, which is 1, plus row 2, which is negative 3. So 3 plus negative 3 is 0. So that's where this 0 comes from here. I'm going to do the same thing for this one, and this one. Here in the second row is 6. Do 3 times 6 plus the negative 2. 3 times 6, that's 18, plus negative 2 is 16. So that 16 goes here. And then in the second row, that's negative 3. Well, actually, it's negative 3. So 3 times negative 3 plus what's in row 3 is 1. 3 times negative 3, that's negative 9. Negative 9 plus 1, that's negative 8. So negative 8 goes here. And then finally, this constant in the second row is 7. 3 times 7 plus this constant in the third row, that's negative 9. 3 times 7, that's 21. 21 plus negative 9 is 12. So that 12 goes there. That's the new row 3 after doing 3 times row 2 plus row 3. Okay, so that's how we do these matrix row operations to solve a system of equations, because we'll be using this to actually solve a system of equations using these matrix row operations here. Okay, the process used to solve a linear system using row operations is called the Gaussian Elimination. And it's named after a mathematician by the name of Carl Friedrich Gauss, who created this type of method for solving a system of linear equations. And it's called the Gaussian Elimination using these matrix row operations here. Basically, the objective is just to get ones along the main diagonal from upper left to lower right, and then get zeros underneath those ones. And then use back substitution in order to find the other two values of the variable, because usually the last row will give you the value of that third variable. Usually it's going to be z. Then to find x, y, and y, you have to use back substitution. So let's look at this one right here. So here we're going to use matrices to solve this system. And we're going to use the matrix row operations that I talked about earlier. Here we got 2x plus y plus 2z is equal to 18. X minus y plus 2z is equal to 9. X plus 2y minus z is equal to 6. And here we want to use this matrix row operations to solve the system of equations here. And bear with me, because this might take a little while. So here, let me write this on a separate sheet. Okay. Okay, so we'll start with what was given to us. 2x plus y plus 2z is equal to 18. X minus y plus 2z is equal to 9. X plus 2y minus z is equal to 6. So that's the system of equations that we have. Okay, now the first thing we're going to do here is convert this to an augmented matrix. So here, earlier we had systems of linear equations, so we were converting those to an augmented matrix. See here. So we know we need brackets with a vertical bar. We write down the coefficients of each of these linear equations one at a time. So for 2x plus y plus z is equal to 18, the coefficient of x is 2. Coefficient of y is 1, and the coefficient of z is 2. The constant is 18. The second equation, x minus y plus 2z is equal to 9. For x is 1. For y's coefficient is negative 1. For z is 2, and the constant there is 9. The final equation, x plus 2y minus z equal to 6. For x's coefficient is 1. For y's coefficient is 2. For z's coefficient is negative 1. The constant is 6. So that's your augmented matrix that you have to convert for this system of linear equations. Now we're going to use matrix row operations here. Okay? Now, there are some things I'm going to do here. I'm going to start off. I want a 1 in this first row, first column. And I got a 1 here and a 1 here. What I'm going to do here is go ahead and interchange the first two rows here. So the first thing I'm going to do here is take row 2, interchange that with row 1. So R2 is going to be interchanged with R1. Row 2 interchanged with row 1. So here's what I'm going to have. Because this is going to lead to this. The first row is going to be 1, negative 1, 2, and 9. The second row will be 2, 1, 2, 18. The third row remains the same. 1, 2, negative 1, and 6. Okay? Now, what I'm going to try to do here is get zeros underneath this 1 right here, because I want 1s along the main diagonal. So I want a 0 underneath this first one, here, here, and here. So I'm going to do 2 matrix row operations here. On the second row, I'm going to do, for me, it's a positive 2, so for me to have a 0, I need to do negative 2 times row 1, and then add that to row 2. Why negative? Because this is a positive. In order for me to make that a 0, I have to do the opposite of this first row, which is negative. So I have to do negative 2 times the first row, and then add that to the second row. Also, I'm going to do a 0 here underneath this first one right here. So also, I'm going to do the opposite of row 1, because this 1 is positive and so is this 1. To make that negative, I have to make row 1 negative plus row 3. Okay, now when I do that, you're going to have to follow along with me on this one. So the first row remains the same. The 1, negative 1, 2, and 9 will remain the same. But on the second row, here's what's going to happen. Negative 2 times row 1. So let's look at row 1. It's this row right here. Each element will be multiplied by negative 2 and added to row 2. So if I do negative 2 times this 1 right here, that's going to be negative 2. Negative 2 plus 2 is 0. And then for this one, this negative 1 times that negative 2, that's going to be 2. 2 plus this 1 is 3. And then negative 2 times this negative 2 will be negative 4. Negative 4 plus this 2 right here will be negative 2. And then 9 times negative 2, that's negative 18. Negative 18 plus that 18 will be 0. So this is what row 2 looks like. Okay, now row 3 is going to change by taking the opposite of row 1 plus row 3. The opposite of 1 is negative 1, plus 1 is 0. The opposite of negative 1 is positive 1. Positive 1 plus 2 is 3. The opposite of 2 is negative 2. Negative 2 plus negative 1 is negative 3. The opposite of 9 is negative 9. Negative 9 plus that 6 is negative 3. Okay? Alright, now what I've noticed in the third row, I have nothing but 3 and negative 3. Those are multiples of 3, so what I can do here is take, let's do this. I'm going to do 1/3 of the third row. 1/3 of the third row. And when I do that, the first row and the second row will remain the same. So I'll bring those numbers over, or bring those elements over. 1/3 of 0 is 0. 1/3 of 3 is 1. 1/3 of negative 3 is negative 1. And the same thing here. Okay? Now again, my main objective is to get a 1 along this main diagonal here. Well, it would be easier for me to put this 1 in the second row, second column, by just interchanging row 2 and row 3. So here, row 2, or I can say row 3, will be interchanged with row 2. I can write it that way. And when that happens, the first row remains the same, which is 1, negative 1, 2, and 9. And then 0, 3, no, take that back, 0, And then this should be a 1 right here because I'm interchanging row 3 and row 2. So in this case here, this goes up here. That's going to be 0, 1, negative 1, negative 1. And this row 2 will become row 3, 0, 3, 2, 0, 3, negative 2. And 0. Okay. I need a timeout here because I think I made a mistake here somewhere. Okay, I'm correct. I'm okay. Well, it should be okay. All right. Now, the last thing I need to do here, I need to get rid of this 3 down here. I need to get a 0 down here. And it's a multiple of 3, so I need to do negative 3 times row 2 plus row 3. And want to see what I'm doing here because I need to get rid of the 3. It's positive, so I need to do negative of row 2 plus row 3. I don't want to mess with row 1 because if I do that, I'm going to have a 1 down here. I'm going to have a number down here, which I don't want. So let's deal with row 2 because I've already got a 0 for x in this first column here. Okay? So now when I do that, here's what's going to happen. The first row remains the same, so this is 1, negative 1, 2, 9. The second row will still be 1, 0, 1, negative 1, negative 1. But the third row is going to change. Negative 3 times 0 is 0, plus this 0 is 0. 1 times that negative 3 is negative 3, plus that 3 will be 0. Negative 1 times the negative 3 will be 3. 3 plus negative 2 is 1. And then 3 times negative 3 times negative 1 will be 3, plus 0 will be 3. And guess what? I'm done. Because now I have 1s along the main diagonal from the upper left to lower right and 0s in the bottom row. That's what I want. Okay, so here's what I'm going to do. I'm going to rewrite this augmented matrix as a system of equations here, which is in this case, the first row will be x minus y plus 2z is equal to 9. Okay, that's the first row. The second row is y minus z equals to negative 1. The third row is simply z is equal to 3. Because that third row gives me the third of the order triple. Now I'm going to use z is equal to 3 and do the back substitution. So here, z is equal to 3 means I can find out what y is by replacing that z with 3. So this will be y minus z, which is 3, is equal to negative 1. And then add 3. You're going to get z is equal to 2. And since z is equal to 2 and y, well, I take that back, y is equal to 2. Y is equal to 2, z is equal to 3. Let's replace the y and the z in the first equation to find out what x is. So in this case here, we got x minus y, which is 2, plus 2 times z, which is 3. That's equal to 9. Now let's simplify this. X minus 2 plus 2 times 3, that's 6, is equal to 9. Then negative 2 plus 6, that's going to be 4. So x plus 4 is equal to 9, which means x will have to be equal to 5. Okay? So in this case here, the order triple will be 5, 2, and 3. That's the solution. That's the order triple that will satisfy this system of equations that we started off with. Okay, now you can do the check if you want to, but I'm going to leave that up to you. Now, fortunately, there is a way that we can find out what the order triple is going to be. And that's basically using the calculator, because the calculator does do matrices, and it does do something else that I'm going to share with you. Okay, so here I have my calculator out. Okay, now the first thing we're going to do here is we want to press this button that says second, and then the button that says x to the negative 1. That's x with that little minus 1 there. You'll press that. You'll get this matrix, because above x to the negative 1 you'll see matrix. Okay, now we're going to put in a brand new matrix here, so let's use our right arrow key to highlight the menu that says edit, and you'll get these letters here from A through I think J, because I think you can put up to 10 matrices in here. We're going to select number 1, matrix A. Okay, now let's look at the situation here. I'm going to move this off to the side. If you look at this, we have the dimensions, because at the top it has these two numbers. That represents the dimensions. You have to put in the correct dimensions in order to put in those correct numbers in there. Now in this case, we got 3 rows, 4 columns. The first number represents the number of rows here. So you'll type in the number 3, and then hit enter, and then 4, and enter, because that's the number of rows and the number of columns. So you type in the number of rows first, and then the number of columns second. And then you're going to enter each row, each element, row by row. Like in this case, the 2, 1, 2, and 18, you're going to enter each one of those one at a time, pressing enter after each element. So we press 2, enter, then 1, enter, 2, enter, 18, enter. Then the second row, we do the same thing. 1, enter, negative 1, enter, 2, enter, 9, enter. Then the last row, 1, 2, negative 1, 6, 1, enter, 2, enter, negative 1, enter, and then finally 6, enter. Okay. Now to get out of this, you want to press second and mode. And then we're going to do something else here. We need to press second and then x to the negative 1 to get back to this. Then you're going to hit your right arrow key to the menu that says math. Now you want to press your down arrow key, because the one that you're going to find is this menu, or this selection that says RREF. Now let me explain what RREF means. I'm going to move this calculator out of the way. RREF means this: reduced row echelon form. What that means is this: you will get a matrix where you will have ones along the main diagonal, you will have zeros below each of the ones, and zeros above each of those ones. So you can have zeros above and below the ones that are along the main diagonal. And this last row represents the coordinates for x, y, and z. That's what reduced row echelon form means. So in this case, you're going to select, which is item B, RREF, reduced row echelon form. by using your down arrow key and highlighting B. Then you're going to press enter. Now you want matrix A because we stored this in matrix A. So second, x to the negative 1, select number 1. Under names, just select number 1. And it'll pop up. And then close your parentheses. Finally, you're going to press enter. Okay, notice in this case here, the 1s are along the main diagonal. We have zeros underneath the 1s and zeros above the 1s. This last column represents the coordinates for x, y, and z. In this case, x is 5, y is 2, z is 3, which is exactly what we came up with when we solved this system of equations by using the matrix row operations. So here, this is a much quicker way of doing this using the calculator, and it's a much easier way to do this, in my opinion. Now, you're free to rewind this tape and take another look at this and just go over this as many times as you need to, so that way you'll get an idea how to do this using the calculator. Okay, so that will conclude this section on using the matrix solutions to solve linear systems.